Good morning, students. Welcome to finite element classes analysis class. Today we shall discuss about the third module, that is beams and shafts. In general, beams find a variety of applications in engineering field, which includes the buildings, the bridges, automobiles in automobile industries, as well as aircraft structures. So beams find the wide applications in these fields. By considering this one, we need to know what is the beam and what are its considerations. A beam is defined as a long, slender structural member whose cross-sectional dimensions are, are relatively small compared to its length. And along with this one, a beam is subjected by a transverse loading, and because of this transverse loading, our beams will produce a significant bending moment. Therefore, the deformed shape of a beam is described by its vertical displacement, that is the deflection, and the rotation, nothing but a slope of the beam. Now, the major necessary thing is to formulate the finite element by considering its degrees of freedom. Let us consider a beam element which is having two end nodes, and each node is having 2 degrees of freedom, and these 2 degrees of freedom are considered as at node 1 it is u1, that is a transverse displacement, that is a vertical transverse displacement, and slope as u2 or a rotation. Similarly, at node 2 we have u3 as transverse displacement and u4 as the slope or rotation. Now, by considering this one, we will define the shape function. The shape function is a function which interpolates the solution between the discrete values obtained at the mesh nodes. And to obtain this, we need to have the lower order polynomials, which are typically chosen as shape functions. Then the shape functions for interpolating displacement on an element can be considered as in terms of zeta, that is -1 to +1, which you can observe in the below sketch. So in the sketch you can observe a element with its extreme points, but for a beam element the slope as well as the deformation must be in terms of a continuous function. Then for this continuous function we need to consider the values of zeta. Then depending upon the loading conditions we can obtain the relating functions. Since the nodal values and nodal slopes are involved, we define the Hermite shape functions which satisfy the nodal value and slope of the continuity requirements. And for your syllabus we will be discussing about the Hermite shape functions for a beams. So what is Hermite shape function? The shape function chosen for a beam element should meet the continuous requirement, which states that transverse displacements and slopes must be continuous over the element. Say this is what for a beam element, not only considering at the end points, there is a deflection even at the midpoint. To obtain these deflections even at the midpoint and throughout the entire element, the necessity thing is that there should be a continuous displacement functions. To obtain this, we need to understand the Hermite shape function. Then the Hermite shape functions are used for interpolation of dependent variables. The dependent variables are nothing but the displacements and its slope. The transverse displacement field is of cubic order expressed in natural coordinates, and it is, we can write it as V of zeta is equal to h1 v1 plus h2 dou v by dou zeta of first element plus h3 v2 plus h4 of dou v by dou zeta of second element. Or we can even write it as h1 v1 is plus h2 theta 1 plus h3 v2 plus h4 theta 2. That is what we have written here. V of zeta is equal to h1 v1 plus h2 theta 1, that is for first element, for the first node, and for the second node we will be having h3 v2 plus h4 theta 2, and consider the above equation as equation 1, where h1 represents the deflection at node 1 and h2 represents the slope at node 1. h3 represents the deflection at node 2 and h4 represents the slope at node 2. Here in the above equation, dou v by dou x is nothing but the slope, that is we can rewrite it as theta 1, that is slope or rotation at node 1. Similarly, dou v by dou x of 2 is theta 2, that is also a slope or rotation at node 2. And v1 and v2 are the transverse displacements at node 1 and node 2 respectively. Also, from the first interpolation functions, we know that x is equal to n1 x1 plus n2 x2, that we can even read it as 1 minus zeta by 2 into x1 plus 1 by zeta by 2 into x2. And we also have the relations of the Cartesian and the local coordinate systems, global and local coordinate system, where x is equal to x1 plus x2 by 2 plus of x2 minus x1 by 2 into zeta. And from this one we can even write it as dou x by dou zeta is equal to Le by 2, where Le is x2 minus x1. And by chain rule of differentiation, we can write dou v by dou zeta is equal to dou v by dou x into dou x by dou zeta. Here just we have replaced with this one. Now dou v by dou x into Le by 2, because we are replaced with the dou x by dou zeta as Le by 2. And we know that dou v by dou x is a slope, so we have considered it as theta into Le by 2. Therefore, V of zeta is equal to h1 v1 plus Le by 2 into h2 theta 1 plus h3 v2 plus of Le by 2 h4 theta 2, and that we can write it as V is equal to h matrix of H into vector Q. Therefore, H matrix H, you can write it as H1 Le by 2 into H2, H3 Le by 2 into H4. This is we call it as Hermite shape functions, and these Hermite shape function we need to derive, and along with this one we have the nodal displacement vector as vector q is equal to v1 theta 1 v2 theta 2. Now for the derivation of Hermite shape function, remember this table for applying the boundary conditions. So we call it as a boundary condition table. Here at zeta is equal to -1, we can consider h1 as 1, and derivative of h1 we can consider it as 0. Similarly, h2 at zeta is equal to -1, we can consider h2 as 0, and derivative of h2 with respect to zeta, consider it as 1. And h3 also we can consider it as 0 when zeta is equal to -1, and the derivative of h3 with respect to zeta is 0. And similarly, h4 is 0 when zeta is equal to -1, and derivative of h4 with respect to 0 is also 1. Similarly, consider when zeta is equal to +1, as h1 as 0, derivative of h1 as 0, and h2 as 0, derivative of h2 also 0, and h3 consider it as 1, and derivative of h3 is 0, and h4 is 0, and derivative of h4 also is 1. Now we shall derive the Hermite shape function for the beam element. To find the shape function h1, as there are 4 degrees of freedom for the entire module, assume a polynomial displacement model, that is h1 hi is equal to ai plus bi zeta plus ci zeta square plus di zeta cube, where I is equal to 1, 2, 3 and 4. Here the each shape function is of a cubic order. Let us have the conditions from the boundary, from the conditions of the table, and that is similar table we have seen that zeta and with respect to minus zeta 1 to plus zeta 1, how the values of h1 and h2 will be varied, and the coefficients we need to determine the coefficients of, that is ai, bi, ci and di, and which can be obtained by applying the above conditions from the table. Now let us consider case 1, that is I is equal to, let I is equal to 1. When I substitute I is equal to 1 in the equation, the above equation at the beginning, h1 is equal to a1 plus b1 zeta plus c1 zeta square plus d1 zeta cube. Consider this as equation 1. Now differentiate the above equation with respect to zeta. On differentiating, we can write it as h1 dash, that is on differentiating the above equation 1, we have b1 plus 2c1 zeta plus 3d1 zeta square. Now for these two equations you apply the conditions. What is the condition? The condition is when zeta is equal to -1, h1 is equal to 1 and h1 dash is equal to 0. Substitute these equations in equation 1 and equation 2. Then we have 1 is equal to a1 minus b1 plus c1 minus d1. Consider this as equation 3. Similarly, on substituting in h1 dash, we have 0 is equal to b1 minus 2c1 plus 3d1. Consider this as equation 4. Similarly, when zeta is equal to 1, h1 is equal to 0 and h1 dash is equal to 0. Substitute these equations in equation 1 and 2. Then we have 0 is equal to a1 plus b1 plus c1 plus d1. Write this as equation 5. And similarly, h1 dash, we have 0 is equal to b1 plus 2c1 plus 3d1. Take this as equation 6. From equation 5, we have a1 plus c1 is equal to minus b1 minus d1. Write this as equation number 7. Substitute equation 7 in equation 3. Then we can write it as 1 is equal to minus 2b1 minus 2d1. Then on simplification we can write it as b1 plus d1 is equal to minus 1 by 2. Write this equation as 8. On adding equation 4 on the equation 6, we have 0 is equal to 2b1 plus 6d1. From equation 9, we have b1 is equal to minus 1 by 3. From equation 4, we have c1 is equal to 0. From equation 3, we have a1 is equal to 1 by 2. Hence, substituting all the values of a1, b1, c1 and d1 in equation 1, we have the Hermite-Shape function, first Hermite-Shape function h1 as 1 by 4 of 2 minus 3 zeta plus zeta cube. This is the first Hermite-Shape function. Similarly, for the second Hermite-Shape function, we consider I is equal to 2. And substituting I is equal to 2 for all a, I, b, I, c, I and di, we have h2 is equal to a2 plus b2 zeta plus c2 zeta square plus d2 zeta cube. Consider this as equation 1. Differentiate the above equation with respect to zeta. Then we have h2 dash is equal to b2 plus 2 zeta 2c2 zeta plus 3d2 zeta square. Now apply the table conditions which have been given in the table. That is, at zeta is equal to minus 1, h2 is equal to 0, and at zeta is equal to minus 1, h2 dash is equal to 1. Now for zeta is equal to 1, h2 is equal to 0, and h2 dash is equal to 0. Then we have, substitute the values in equation 1. Then we have 0 is equal to a2 plus b2 plus c2 plus d2. Write this as equation 5. And similarly, for h2 dash is equal to 0, then we have 0 is equal to b2 plus 2c2 plus 3d2. Write this as equation number 6. From equation 5, we have a2 plus c2 is equal to minus b2 minus d2. Write this as equation number 7. Substituting equation number 7 in equation 3, we have 0 is equal to minus 2b2 minus 2d2. From the above equation, we can write it as b2 is equal to minus d2. Write this as equation number 8. Adding equation number 4 and 6, we have 1 is equal to 2b2 plus 6d2. Write this as equation number 9. Solving equation 8 and equation 9, we get d1 is equal to 1 by 4. And from equation 9, we get b1 is equal to minus 1 by 4. Hence, substitute all the values of a2, b2, c2 and d2 in equation 1. On substituting, we get the second Hermite-Shape function, that is h2 is equal to 1 by 4 of 1 minus zeta square plus zeta cube. Similarly, following the same conditions for the remaining two Hermite-Shape functions, that is following the same procedure, similarly we'll get h3 as 1 by 4 of 2 plus 3 zeta minus zeta cube, and h4 as 1 by 4 minus zeta minus 1 by 4 minus 1 minus zeta plus zeta square plus zeta cube. So these above h1, h2, h3 and h4 are called as Hermite-Shape functions. Then the Hermite-Shape function can be used to write the deflection in the form of v is equal to h1 v1 plus h2 dou v by dou zeta of 1 plus h3 v3 plus of h4 dou v by dou zeta of second element, but v is equal to h1 u1, and where the second derivative we can write it as le by 2 h2 u2 plus h3 u3 plus le by 2 h4 u4, or it can also even write it as v is equal to h into u, where h is equal to h1 comma le by 2 h2 comma h3 comma le by 2 of h4. This is the Hermite-Shape function derivation, and it is also an important derivation for the beam subject. Next, we will go for derivation of stiffness matrix of a beam element. See how we have derived the stiffness matrix for bars and truss problems. In a similar manner, we will go for the derivation of stiffness matrix for beam element. Let us consider a strain energy for a beam element, and which is given by UE is equal to EI divided by 2 integral of LE of dou square v by dou x square whole square into dx, where E is Young's modulus and I is the moment of inertia of the beam element. As we know, dou v by dou zeta can also be written as dou v by dou x into dou x by dou zeta, or we can write it as dou v by dou x is equal to 2 by Le into dou v by dou zeta, because we know that dou x by dou zeta is nothing but Le by 2. Then we can write the equation as dou square v by dou x square is equal to differentiate. We have considered this one. Now if I differentiate, we will be getting as 4 by Le square into dou square v by dou zeta. Also we can write it as v is equal to h1 v1 plus Le by 2 h2 theta 1 plus h3 v2 plus Le by 2 into h4 theta 2. Therefore, dou square v by dou x square can be written as 4 by Le square into dou square by dou zeta square of h1 v1 plus Le by 2 h2 theta 1 plus h3 v2 plus Le by 2 into h4 theta 2. And on simplification, we get it as 4 by dou square v by dou x square is equal to 4 by Le square of dou square h by dou zeta square into v1 plus Le by 2 into theta 1 into dou square h2 by dou zeta square plus dou square h3 of dou zeta square into v2 plus Le by 2 into theta 2 of dou square h4 by dou zeta square. Close the bracket. On simplification, we get dou square, the equation says dou square v by dou x square is 4 by Le square of dou square h1 dou square h1 by dou zeta square into v1 plus Le by 2 into theta 1, that is dou square h2 by dou zeta square plus dou square h3 by dou zeta square into v2 plus Le by 2 into theta 2 into of dou square h by dou zeta square. Let us consider dou square v by dou x square as C into C into vector matrix C into vector v, where C can be the above equation C, where can be written as with respect to the Hermite-Shape functions. Substituting the above equation in the equation 1, on substituting we get the strain equation as 1 by 2 integral of Le of vector V transpose into EI C transpose into C matrix C into vector V dx, or we can even write it as 1 by 2 integral of Vt into Ke of vector V into dx, where Ke is equal to integral of Ee into C transpose into C matrix C dx. On simplification, on substituting the value of h1 is equal to 1 by 4 and h2 as 1 by 4 1 minus zeta square into zeta cube, and h3 and h4 values in the above equation, and differentiating c twice, we get c is equal to 1 by le square into 6 zeta minus le into 1 minus 3 zeta minus 6 zeta le into 1 plus 3 zeta matrix. Therefore, on substituting the values of C transpose on C, we have the matrix as integral of minus 1 to plus 1 C transpose into C d zeta as 2 by Le to the power of 4. On substituting all the values of h1, h2, h3 and h4, we have 12 6 Le minus 12 6 Le and 6 Le and 4 Le square minus 6 Le and 2 Le square minus 12 minus 6 Le 12 minus 6 Le and 6 Le and 2 Le square minus 6 Le and 4 Le square. Therefore, element stiffness matrix can be written as EI divided by Le cube, that is 12 6 Le minus 12 minus 6 Le and 6 Le 4 Le square minus 6 Le 2 Le square minus 12 minus 6 Le 12 minus 6 Le 6 Le 12 2 Le square minus 6 L 4 Le square. This is what the stiffness matrix of a beam element. Also remember the load vectors for a beam element when subjected by a point loads or a UDL. Load vector due to point load can be written as vector F can be written as F1. At node 1 I can take it as force F1 and moment M1. Similarly at node 2, force F2 and moment M2. And force I can write it as P by 2 and moment I can write it as PL by 8. And similarly at node 2, P by 2 and minus PL by 8. And whenever it is a UDL, we will write it as the forcing function as PL P naught L by 2 and moment P naught L square by 12, and at the end also we can write as P naught L by 2 and P naught L square by 12. And remember this nodal force and bending moment table for solving the problems. In the next class, we will be considering the table as well as the stiffness matrix formulae, and we shall solve the problems. Thank you.